Okay, we are recording. Fantastic. So let me go in here. Very good. How do I make? How do I make full screen? Where is the presenter viewing here?
It's the three dots here.
Fantastic. Thank you. And does this work?
And for the hand over the microphone further.
That's very important. Thank you.
So our first speaker is Frederi Viens, my statistics and farming advisor. Mentor.
So everybody, if you can, I don't know if you can hear as we pass the mic over.
That is only for the camera.
Oh, it's only for the camera. Okay, well,
Because we're having technical issues.
I'd like to make sure that everybody knows that it's my pleasure to present to you Dr. Pablo Giuliani.
Thank you.
Thank you.
When you want to comment, you let me know because I need to share a screen.
All right, thank you. All right, thanks everybody for coming here. I'm absolutely delighted and honored to be here today to present a little something here as we get this summer school started. We're going to talk about uncertainty quantification so folks have realized. Hi, Alexandra, I can see you there. So she'll be speaking later this morning or this afternoon. Yeah, afternoon. So we have this great team of folks that Dr. Giuliani has put together so that we can understand more about uncertainty quantification, especially nuclear physics, and how to set it up numerically, because sometimes it gets extremely hairy to do things, and we're going to waste a lot of time and computational effort if we don't know some of these new methods that these folks will be presenting. But before we get into any of those things, excuse me. My name is Frederi. I'm on leave for Michigan State. I'm a professor at Rice University in the statistics department there, and I love Bayes and uncertainty quantification. So before we can get into all the complicated stuff later in the summer school, what I would like to do is to present. I have actually only 8 slides here after this one, and the last 3 slides are actually optional. So we don't have a whole ton of slides to present, but they're a little bit dense because I'm old school, and I even remember when the men landed on the moon in 1969. That's how old I am. So you'll see that it's very old school. I don't really remember because I was too little to remember, but my mother remembers that I was there watching the TV. The little TV, 1969, imagine. 69, very good year, by the way. So the story is that Thomas Bayes. How many people here have heard of Thomas Bayes? Raise your hand. Okay, most folks have heard of Thomas Bayes. How many people here have heard of Bayesian statistics? Everybody, yeah, everybody I think raised their hand. So Bayesian statistics is named after Thomas Bayes. I want to say a couple of things about the history, since we don't have a lot of slides to cover. And also, this is supposed to be a school which is very interactive. So even though my presentation doesn't include specifically an interaction part, like we don't have an interaction part in our linear model sort of thing here for this particular presentation. But feel free, thank you for smiling. So feel free to interrupt me at any time with any comments, questions, remarks, or random comments about something else. That works too if you want. But Thomas Bayes, a little bit of history. He was a Presbyterian minister who, let's see, I think I have that on the next slide actually. So yeah, plan of this tutorial is we're going to start with an introduction, Bayes 001, so we understand some of the underpinnings. Then there'll be a primer on Bayes, which will be most of this presentation, Bayes 101. And then if we have time, we'll go through sections 3 and 4 here on Bayesian model averaging and Bayesian model mixing. But model mixing, Alexandra is going to be doing a whole presentation on that. And so I'm going to say a little bit more about why we're doing that twice in a second here. But before we start, let's see, this is a pointer, so there should be a little light in here. Yeah, there we go. Who was Thomas Bayes? He was born in this year, presumably, because it was a long time ago and we can't really remember anymore. And this is when he died. He was a Presbyterian minister in a little town in southeast England, a very wealthy little town called Tunbridge Wells, which is like, anybody here drink Vichy water or San Pellegrino? Anyone? The couple of drinkers of San Pellegrino. Okay, so you guys know about mineral waters, right? But I mean, it used to, now it's kind of gone out of fashion. Mineral waters used to be a real thing, and people would actually travel, many miles, long distances, in order to get to towns where this mineral water was actually coming out of the ground in a natural form. And especially before people were able to bottle things in an industrial way, this was the only real way that you could actually get the benefits of some of those mineral waters. And the town of Tunbridge Wells was one of those places, one of the few places in the UK where rich people would travel from all over Europe, to go to Tunbridge Wells, to drink the mineral water and do other things that make you more healthy. And Thomas Bayes was the minister for this town. And so that's what his job was. Now, another thing about Thomas Bayes, and again, we have time, so I'm going to tell you a little more about Thomas Bayes because it's really, his story is really interesting. Thomas Bayes was able to practice mathematics because he was rich, and the only job, he didn't really need a job at all. He came from a wealthy family. They made their money, I'm going to use an English word here, which maybe folks don't. Do you know what a cutler is? Cutler. Raise your hand if you know what a cutler. Yes. One person knows what a cutler is somebody who makes cutlery, especially knives. Okay, so that's what cutlers are. And the best cutlers in the world at the time were from the Sheffield region. Why is that? Because in Sheffield, England, there was the best coal and the best iron ore, which you could use to make the best steel and then make the best cutlery, at least in the Western world that people were aware of at the time. It's quite possible that in Japan, people were making better knives than they were in Sheffield, but in Sheffield, in Sheffield, one of the most prominent families of cutlers was the Bayes family. And so that's why Thomas Bayes was so rich, because his family was extremely wealthy from being the best cutlers in England or something like that. And so he didn't need a job, but he was a very smart person. I think he had a degree in philosophy, which many people had at the time because degrees in other fields didn't really exist. So everybody had a degree in philosophy, but he was a theologian, maybe he had a degree in theology. He was a theologian, he was a very, religious person, Presbyterian minister. He actually, had his whole entire congregation. Nonconformist, right? He was not part of the Church of England. So nonconformist means because he was Presbyterian and not an Anglican, nonconformist Presbyterian, he was thinking in non-standard ways. So it's not an accident that we owe this whole theory of Bayes to somebody who was a nonconformist Presbyterian minister, right? Because if you're a Presbyterian minister, that means you have extra time that you can spend doing other things. And if you're nonconformist, you're not going to conform to whatever people were thinking at the time. This nonconformity, hold on a second. Has anybody ever heard of the law of gravity? Law of gravity? Raise your hand. Okay, who do we owe the law of gravity to originally? Y'all know? I'd like to hear an answer. Newton? Isaac, right? Isaac, the man, right? See, he wasn't a very nice person, but he was a real genius. He was actually not a nice person at all. Okay, let's be clear. You might have heard of Leibniz, who was a wonderful person who formalized Newton's calculus, and Newton destroyed his career. And so that's the kind of person that Newton was, right? After Leibniz actually helped everybody understand what a genius Newton was, Newton destroyed Leibniz's career. Okay, so, but excuse me. But notwithstanding, because Thomas Bayes was such a man of science, and even the notion of science at the time was not even clear, but he was a man of science. He realized that Isaac Newton's theory of fluxions, which is here on the slide, his doctrine of fluxions, which was differential calculus that Newton invented, he invented differential calculus. And the people in the Royal Society, he was the president of the Royal Society. And the people in the Royal Society did not understand his theory of fluxions because he was too smart to be able to explain it properly. So who do you think? And oh, by the way, so maybe we're not going to get to my presentation at all. This history is so fascinating. Listen to this. And it also has to do with diversity. I'm going to say a word about diversity in a second here. Because we want, so if you look at the rules of behavior in FRIB, you have to be cognizant of diversity. I'll say something about that in a second. But here's the thing. What's the best public university in the United States? You may have an opinion about it. Raise your hand and give me your opinion. Best public university in the United States. Don't say University of Michigan, okay? Right.
Michigan State.
Yeah. Berkeley, yes. Okay. So, yeah, UC Berkeley. It's the universe's best university, something like that. Okay, Berkeley. Who is Berkeley named after? Berkeley, yeah. Berkeley. First name? George Berkeley. Right. George Berkeley was a bishop. He was an Irish bishop. The town of Berkeley was named after the university was named. So the university existed before the city. Did you guys know that? Yeah. Anyway, so George Berkeley was an Irish bishop who was also, just like Thomas Bayes, a mathematician and a scientist and a philosopher. And George Berkeley was more advanced in his career than Thomas Bayes at the time, when Thomas Bayes was trying to defend the theory of fluxions, the doctrine of fluxions. And George Berkeley just didn't believe it, and so he had the whole entire Royal Society against Isaac Newton, even though Newton was the head of it. And this paper, Thomas Bayes only published one paper in his entire life. This one, An Introduction to the Doctrine of Fluxions and a Defense of the Mathematicians against the objections of the author of The Analyst, 1736. So he was only 35 years old when he published this. He published it. This is the reason why the differential theory of calculus became accepted. It was Thomas Bayes. This is the kind of genius we're dealing with here. It was Thomas Bayes who explained to the entire scientific world, Western world at the time, which was, the center of that was in London, or maybe Germany too, but at least in London, why it was correct, why it was not nonsensical to talk about infinitesimals and all these sorts of things. It was Thomas Bayes who figured that out. On the basis of this paper, he was then inducted into that society, the Royal Society, and it was only, look at this. Oh, and I wanted to mention, so the question of diversity is like this. George Berkeley was actually a horrible person. He actually owned land in the United States, and he captured Native Americans and made them into slaves on his land. And then he wrote treatises to explain why they were savages, and it was okay to do that. Now, the University of California at Berkeley, which is named after George Berkeley, sits on land that was stolen from Native Americans, and UC Berkeley accepts that now and is happy to tell anybody that this is the case, but they still won't change their name to something else than George Berkeley's name. Even though I think at University College Dublin or someplace like that, there's a whole entire wing of the university where they used to be called Berkeley, and now it's called something else. They decided that Berkeley's past as not just a slave owner, like in America we had lots of slave owners who also did good things and maybe worked against slavery later on in their lives. No, George Berkeley, no, not like that. He was sure that it was a good thing, and the Native Americans were savages. So the author of The Analyst, that's George Berkeley. This is George Berkeley. He wrote a book called The Analyst, and he was a mathematician, and he was also maybe a worse person, probably a much worse person than Isaac Newton. But having said that, Thomas Bayes did not like George Berkeley, defended Isaac Newton, and people have forgotten that this is an extraordinary important contribution to science. We might be much further back than we are today if Thomas Bayes had not been able to explain to everybody in the room over there what these differentials were about. Yes, sir.
I want to mention that my professor from calculus, from the first time that he talked about derivatives, he asked us all to think what inventions we know before 1700s, basically before calculus, and how inventions you can mention after. And it's like, yeah, before it's like we have the wheel and fire and a couple of things, but after calculus, it's like
Technology,
a nice thing to think about.
Yeah, technology comes from calculus. Yes, I agree. And Isaac Newton, as bad as he was, I don't think he was a slave owner, and he was a real genius. And Thomas Bayes recognized it. And it's like we're trying to emulate what Bayes is doing. In fact, emulators, we're trying to emulate what Bayes is doing. And so let's emulate the fact that he was able to explain to the whole world that there was the gem that they couldn't see. And so that's the story there. And just on the topic of diversity, we just realized not very long, a couple weeks ago, that the dates of this summer school were actually not optimal. There's probably a couple people in the room who are devout Muslims. Well, the Feast of the Sacrifice. So we want to be open to all cultures and make everybody feel welcome and included. The Feast of the Sacrifice, which is one of the most important festivities in the Muslim world, it was supposed to fall on. In fact, in Saudi Arabia, it falls on the 29th. So in the Arabic part of the world, in North Africa, it falls on the 29th of June, which is Thursday. But because of the way that the moon works, you have to be able to see the moon in the sky in a certain position in order to declare that the Feast of the Sacrifice is on. Well, a couple weeks ago, they decided it had to be the 28th here in the United States. And so that's Wednesday. So there's some folks who will not be able to attend this workshop because of this slight issue that we didn't see that thing coming, right? So, and in fact, I won't even though I'm not a devout Muslim, I won't be here on Wednesday also for that reason. So, yeah, so let's just keep in mind that we want to be open to all cultures. And, you know, when you see some of us disappear on Wednesday, it's not because we're lame, it's because the organizers of this conference didn't quite figure out that this might become a problem. Okay, so with that all said, so if you guys have had enough about this history of Bayes, etc., we can move on to our introduction of what it means to be to try to understand Bayesian statistics. And you know, you can read the slide. It's dense, I know, because I don't know how to make nice slides like Dr. Giuliani. What's really cool about Bayesian statistics is that it's a complete and intuitive inferential approach. Inference means, for instance, that you can have point estimation of things that you're interested in. If you have a model, I think everybody understands what models are. And if you have a model, there might be some parameters there, or you might be trying to reconstruct data or maybe predict data or something like that. Reconstruct missing data, extrapolate to predict new data, estimate parameters. You can look for point estimation, which tells you here's the best guess for what the value should be. Bayes, of course, to do that. It's intuitive in terms of model validation and hypothesis testing. I don't want to be getting too much detail here, but intuitive meaning that I think everyone has a notion in their mind of what a probability is. When you flip a fair coin, you know that there's a 50-50 chance that it's going to fall on either side. When you're sitting in 2016, in November 2016, and Hillary Clinton is 63 points up in the polls, whereas Donald Trump is, 40 or something like that, 35, or there were two other candidates. And so, and then if you're a probabilist and you think carefully about what that means that it's pretty even, right? And then we should be surprised if Donald Trump actually wins the election at that point. So that's what probability tells us. 2-to-1 ratio, 67 to 33, that's a 2-to-1 ratio. We understand probability. Nobody should be surprised that Donald Trump won the election in 2016 because that's what his odds were. His odds were 1 against 2. So of course, if you flip a 3-sided coin, the chance of landing on one of those 3 sides is actually not very small, right? Probability, everybody okay with probability? Yeah, okay. So that's why these things are intuitive. Physicists, I believe they love probability. Oh, one other thing, yeah, I guess I have until 12.
You have no.
Until 10 o'clock.
Yes.
Yeah, until 10 o'clock. But please interrupt me so we can have a discussion too. Let's see. Let's maybe keep going here, and I'll think of another funny thing to say in a second here. There's precise uncertainty accounting. You don't just get a point estimation. You get a full parameter distribution. You get full distribution of parameters. Distribution of parameters. You guys have all heard of the bell curves, right? Everybody's seen a bell curve. That's a type of distribution where the tails go to 0 pretty fast because it's unusual to get very large values on either side. When you have it can be extremely unusual if you go far out. If you've heard of the concept of 6 sigma, it comes from there. I think it's idiotic, but it comes from there. If you know about 6 sigma, it's like people who think they're so exceptional that they're beyond the tails of the normal, So yeah, well, there's this the first pick of the NBA first pick of the NBA draft. You guys heard about the story recently? It's a French guy. Like, it's the first time that a French person has been the first at the very top of the draft. And this guy's 7'4", and they say he's the new LeBron James. That's 6 sigma. Okay. So, all right, and he's 19 years old. Oh, that reminds me. So we're going to sorry. Okay, so here's the thing. You're going to see in these slides, if we get to them, that there's a certain amount of notation. Even within the last 3 slides that I have here, which are left over from 3 years ago, and the first 4 slides, which I think are the ones I really want to cover, you're going to see that there's a slight difference in letters that we use for the same concepts. When Dr. Sankowski, no, you're not a PhD, no, just Ms. Okay, sorry. So when Ms. Alexandra presents does her presentation this afternoon on model mixing, you'll see that she will be using a slightly different notation than I am. And even within my own slides, there's slight variation in notation. So why are we doing that? If we're trying to teach a group of people who don't understand notation, it's a bad idea. But here we have, what do we have? Mathematicians. Mathematicians, raise your hand if you're a mathematician. I'll raise mine because I have a PhD in math. There's 2 or 3 people in the room. Statistician. I'll raise my hand because I've been working in statistics. Yeah. A couple statisticians. Yeah. Physicists. Anybody physicist here? All right. Any engineers? If you consider yourself an engineer because you're an experimental physicist, Please, by all means, raise your hand. Yes, sir. Yeah. Okay, so these folks are folks who, do you have a degree in engineering? No, physics. Yeah, but you're an engineer. No, same. I'm a financial engineer. Turns out, if you know I have a degree in. So we know notation. Am I right? Okay. Louis de Broglie. Everybody heard of the Schrodinger equation? Yeah. 1926. Am I right? When it was published, 1926. What happened before that? Where did it come from? How did he get the idea? There's a story. There's a reason I'm telling the story. So a lot of the stuff that we're doing has to do with the Schrodinger equation. It's too hard, too complicated to do numerically. So with these many body problems, we have to do it. If it's too hard to do it theoretically, you have to do it numerically, and even then it's hard. But where did it come from? Anybody know? So where did the notion of wave for particles come from?
I don't know how to pronounce his name correctly, but de Broglie.
That's right. Louis. Okay, so since I'm a French citizen, I know how to pronounce his name. Louis de Broglie. Oh, de Broglie. And he's from the very northern part of France, which is near Belgium. So I think that's why they pronounce it funny. Yeah, his name is de Broglie. It's spelled D-E-B-R-O-G-L-I-E. De Broglie. No, de Broglie. First name Louis. So you can call him Lou. Just call him Lou. And so he defended his PhD, I think, in 1924. And his PhD was about the wave properties of electrons. And that's where the idea came from. In 1925, it was verified experimentally. In 1929, this is, I think, 5 years or 4 years or 5 years after he got his PhD, he got a Nobel Prize for what he discovered, because it was verified experimentally like a year later, and it changed everything, including bringing Schrodinger to realize that everything's a wave. Everything's a wave. That's Louis de Broglie, who first says it had to be so for electrons, and that's why he got a Nobel Prize like 5 or 10 years before Schrodinger got his own Nobel Prize for rediscovering the same thing and applying it to other stuff, right? So, so Louis de Broglie, impressive guy. Why am I bringing Louis de Broglie? Louis de Broglie, sorry. Because he had this nasty tendency. So he was like a child prodigy, right? He gets a Nobel Prize when he's like 35. And he had this nasty tendency that he would force his students to switch notation all the time. And he did it for pedagogical purposes. And so that's one of the reasons why, I mean, I'm not trying to emulate de Broglie. I mean, I might be able to emulate Schrodinger maybe, but not de Broglie. So that's why we're going to go through some of this stuff. Each one of your instructors is going to have slightly different notation, because we want folks to focus on the concepts rather than the letters. So here we go.
It's completely on purpose. We had all the exact same notation, but we met on the weekend and said,
"Oh my God, we were so
consistent."
We like, "Oh my God, we're consistent." Let's change it. Yeah, right. That's right. Yeah, yes, quite right.
Yeah, that's exactly what happened.
Exactly what happened.
Yeah.
Okay, and so we get probability statements about uncertainty conditional on the data that we have. So and so you're going to see notation starting to come in the next slide, which will force you to think about what all these things mean in terms of what's written on this slide. I just want to point out that there's a difference between so Fisher, who was the person who invented the hypothesis testing and a lot of the methods that we use in ordinary classical so-called frequentist statistics. Today, we're trying to move away from frequentist statistics, coming from Fisher and what he told us to do, because it turns out that Fisher was also a horrible person. There was a building at University College London, I think, or someplace in some important university in London. They just took the name off the building because he was a eugenist. You guys know about eugenics, right? Yeah. And so he was like trying to figure out who was feeble-minded, and the darker your skin was, the more likely you'd be feeble-minded, and so then he was going to actually forcefully eradicate your race and that kind of stuff. So that was and he was an apologist for Nazism because he thought that they would be helpful in eugenics as well. Very, very horrible person. That's Fisher. So we're happy to be getting away from frequentist statistics and doing Bayes instead. As far as we can tell, it's too long ago, so we don't really know what kinds of bad things Bayes did. We only have good things to say about Bayes. There's no history, it's bad stuff that he did, so we're going to keep his name. Yeah. So here's the difference. And you can see that there's 3 lines here, and there's how many? 1, 2, 3, 4. There's 5 lines here, right? For the interpretation of confidence intervals in classical statistics, and there's 3 lines in the Bayesian case. That's because it's easier to explain in the Bayesian case than it is in the frequentist case. let's read it. Let's see if it makes more sense. Bayesian credible interval. By the way, confidence interval in Bayes is called credible, not confident. Yeah. A Bayesian credible interval, conditional on all the data, and based on our belief. Bayes was a Presbyterian minister, he believed in stuff, right? So based on our belief in probability modeling, there's a 95% probability, again, that's the keyword, right? That the true value of a parameter is in the quoted credible interval. So that's what it means to have a credible interval. You have a parameter, you don't know what it is, you quote a credible interval with a 95% credibility level of credibility, and you say, well, that means that chance that the number is in that interval I'm giving you is 95%. That's the chance. That's how easy it is to explain it in Bayes. Check out what it means in frequentist. By repeating a random experiment many times with enough data each time and producing a confidence interval for a parameter each time, we know that 95% of these intervals will contain the true population parameter. So it forces you to have the ability, if you want to get real good about it, it forces you to have the ability to repeat your experiment infinitely many times. So like I always say, for instance, when you're working in certain areas like, for instance, climate change, well, there's no planet B. We only have one planet, right? So we can't repeat the experiments. So we have to, track what the planet's been doing. There's one single experiment. How about in nuclear physics? How expensive? You press the button on the F-Rib console, right? $200,000 every time you press the button. Is that right? Is that about the number? Yeah. Yeah. Another $200,000. So yeah, it's expensive, and so it's better to use Bayes. That's what I'm saying. Yeah. So all right. Okay, here's our primer on Bayes. Don't feel. So here's the other thing. I think that it's probably paraphrased in the rule of conduct in FRID, but this is a no judgment zone. If you think I'm full of BS, you should let me know. BS stands for Black and Scholes. That's the fundamentals of financial mathematics. So just let me know, because as we know, Black and Scholes is BS. Okay, so has anybody watched the movie Ridicule? Raise your hand. Anybody watched the movie Ridicule? You should watch it. Okay, I'll explain it. All right. So feel free. It's a no judgment zone, which means that there's no such thing as a stupid question. If you come to my farm, which is a half hour from here, and you want to help me with farming things, and you ask me questions, they will be stupid, and I will let you know, and I'll make you feel very bad about it. But that's at my farm. No, this is at Fred. It's a no judgment. There's no judgment here. So anybody can interrupt with questions. There's no such thing as no. All the questions are good, and the instructors have to answer them as part of the deal. Right? No judgment zone here. Everybody. Okay. So any notation here that you don't quite grasp, let me know. So I have an example here which is completely made up. I have no idea if any of this is meaningful at all. Some of the people in the room are not nuclear physicists, so they may tell me that this is complete BS, but just bear with me, it's just an example. Okay? So there's such a thing as nuclei in physics. This is calcium. Calcium has a certain number, and Professor Juliana is going to explain this in more detail. Calcium has a certain number of protons. 20, right, is the number of protons, and there could be more than 20. There's more than 20 neutrons usually, and there can be much more than 20 neutrons. And in this case, there's 42 neutrons. That's why there's the 62 there. Everybody see? So you got 42 neutrons here in this calcium isotope. Isotope means one version of calcium with a certain number of neutrons. 60 of these nuclei here in this calcium, 40 neutrons and 20 protons. And the amount of energy that it takes to take two of these neutrons, to take a pair of neutrons and yank them out of the nucleus. The nucleus is this big ball full of neutrons and protons. You find two of these neutrons, you try to yank them out of the nucleus, and that's the amount of energy that you need to just be able to barely do that is the separation energy, right? The nuclear physicists, you know that I don't know this stuff, so you can stop me when I say it's something wrong. And the events that I'm interested in, the event of interest that I'm interested in this example is, it's the event that it takes at least 5 kiloelectron volts to separate two neutrons out of the calcium 62. That's probably totally wrong, but it's so unstable that it doesn't take a lot of energy. Kiloelectron volt is a measure of energy. It doesn't take a whole lot of energy to take two neutrons, we think, but we'd like to know what's the chance really that it only takes this tiny amount of energy, to separate these two neutrons from this calcium 62. The event B, calcium 60 has been observed. Again, this is completely made up. But in this example, I'm saying that calcium 60 has been observed that it only takes 10 kiloelectron volts of energy to separate two neutrons from the nucleus of calcium 60. Everybody with me? So we know that B is true. We know that B is true. That's our data. It takes just barely more than 10 kiloelectron volts to separate two neutrons from calcium 60. But we haven't been able to observe calcium-62 yet because it hasn't been experimentally, created or whatever. This is like 20 years ago before EFRB existed. And so we're not really sure that this might be true, but maybe it's true. And we'd like to know what the chance is. So the question is, find the probability of observing A, given that we know that B happens. Everybody see? Yeah. So we know that this one can be separated easily. It's probably going to be easier a little bit because this is a little bit more unstable nucleus in order to separate it over here. So that's why I put 5 instead of 10. But we really like to know the chance. And so method is to do this. Step 1 of the method, we have to decide on the likelihood of observing the B that you can separate 2 nuclei with 10 electron volts from calcium-60, given that in your imaginary world, A has happened. In other words, the one that we're interested in measuring the probability. So you have to come up with a model. You have to come up with a model for the probability that B is true, given that A might be true. Yes?
Just as a comment, the first one should be around 1 MeV and the second one should be around 3 MeV.
See, I knew that.
Yeah, I know, just mentioned. No problem, no judgment, son.
No judgment, right?
Yes, without judgment.
At least I made up an example that's relevant to nuclear physics when I have no training at all. Okay, so we have to come up with a model that if it turns out that A is true, what's the chance that B might also be true? And model for that. So this, we have to work with real nuclear physicists in order to come up with this number. But let's say we come up with it. This is called the likelihood. And for good measure, we also like to know the likelihood of B being true, given that it has been observed that A is not true. So you want to have those 2 alternatives. What if A is true? Then what's happened to the chance of B? What if A is not true? Then what happens to the chance of B? You need those 2 numbers in order to do the full analysis. In the second step of your method, you're going to decide on a frequency of the thing that you're hoping to calculate. You have your own idea. You have your own idea. So like, given what Dr. Giuliani has said, this probably is close to 100%. I mean, it's 100%. But the chance of A, because the 5 is so small.
Well, it could be unbound and then it's less than 0. If the thing just breaks up.
Okay, so not totally clear. All right. So anyway, so you're a nuclear physicist. You have some idea of what's going on in the world of particles and nuclei, and so you have your own idea of what probability of A really is. You're looking for that number, but you have your idea of what it might be. You went to Tunbridge Wells. You drank the Kool-Aid. I mean the water in Tunbridge Wells. Thomas Bayes spoke to you through the grave. Actually, he's buried in London. So then you have to travel to London to go to the grave of Thomas Bayes. He speaks to you and he tells you what that number should be. And because it's Thomas Bayes, what do? You believe it. Pardon me?
To write it down.
You write it down and you believe it. That's right. Yeah. So you find a way of figuring out what your idea of this probability is. That's your prior information on the thing that you're looking for. But you want information about this, knowing that B happened. And here, notice that, so this vertical line means conditional on, probably B conditional on A. This is not conditional. You don't assume anything about B, whether B is true or false. You just want to find out what that number might be, unconditionally on whether B happened. And Thomas Bayes tells us, well, here's how you do it. Here's the formula. It's not very complicated. You can see. You've seen it before. Everybody seen this formula before? Yeah. The denominator. So since B has happened, the probability of B is just. It's a little harder to. I'm going to explain that what the denominator does in the second formula down here. But for this numerator, you take I should have tried to use colors on these slides, but since I'm old school, I can't even do that. You take your likelihood, you multiply it by your prior, and then you divide by some normalizing factor, which you compute this way. And that's the answer. So it's interesting. It's so simple. It's so simple. So there's a drawback to things which are simple, is that when you try to apply them to lots of different things, then the methods to actually compute things can be complicated. That's why we're here today. But the idea is so simple. Here's the idea. Again, you want to calculate the chance of something happening that you don't know about, given B, which is something which you know has happened for sure because you've observed it. You want to compute this conditional probability. Bayes says it's a very simple inverse problem. Just take the conditional probability in the other direction, multiply it by your prior, divided by some normalization factor because there's much probabilities to add up to 100%. And that's it. That's it. That's it. So it's just really the numerator, which is, you compute this numerator. You can also do it for A complement, and you're going to get the same formula there. Just compute the numerator. What kind of computation? We're multiplying 2 numbers together. Like that's the simplest possible. Other than addition, you can't do anything easier than multiplication. So that's how simple Bayes' rule is, but it works. The likelihood, so just summarizing, the likelihood is modeled for our reality contingent on what might happen. So likelihood, let's go back. our reality is we know B happened. What is the chance of B happening contingent on what might happen? So likelihood is a model for our reality contingent on what might happen. The prior is the frequencies of what might happen. It can use external data. It's whatever your opinion is. You can go and use external data, like ideas from other people, in order to figure out, what your prior is on what you're looking for. And this is the summary of what these two things are, likelihood and prior. This thing I didn't write on the slide, but this is called a posterior. This is a posterior probability. This works for random variables too. Everybody heard of random variables? Random variables, raise your hand. Random variable, okay. So random variable, these are just events. So either an event happens or it doesn't happen. A random variable is kind of like an event, but an event is like a two-value random variable. Either it's a 1 or a 0. A random variable can have lots more values, so it's more complicated, but it has the exact same flavor. You have random variables here, x and y, rather than just your a and b. And we're interested in the so-called probability densities of these two random variables here. And Bayes tells us that if you're looking for the conditional probability density of x, which is the thing that you would like to know about, given y, which is the thing that you actually observe the value of your random variable y. In order to compute this problem, here I use a notation here, a simplified notation. You really should put these subscripts under there. Notice that so this is a point I wanted to make in terms of notation. Nuclear physicists will hate this because you will try to use the same typesetting for both the name of the random variable and the possible values that it could take. That's a mistake in mathematical notation. The random variable has all sorts of values, but if you happen to know that the random variable y is equal to the value of little y, then you should distinguish between those two letters. That's why we write random variables in capital letters, and their actual possible values, like the one you've observed, little y, a lowercase letter. So that's what we do. And so that's why there's a subscript for the names of the random variables, and there's inside the formula, there's the names of the values that they might take. But see, if you look at here, it's the conditional probability in the other direction multiplied by the prior probability of the thing you're interested in. This is the exact same numerator as we have up here. It's the exact same formula, except it uses densities instead of probabilities. Densities are like rates of probabilities, so it's the same type of object. And so that's why the formula also works. And you have this denominator here, which instead of doing a sum, you have to do an integral because these are densities. But what really matters is, since little y is known, and what you're interested in is what happens to this expression as little x varies, anything that happens to depend only on little y is not really important to you because you're only looking for the variations in frequency with respect to little x, the thing you don't know about. Little y is fixed. And so this denominator here, you can see that we integrate, I replaced the little x by a w, and I've integrated it out. So the denominator only depends on little y. Am I right? Everybody see? You guys know Leibniz's notation of calculus, right? For the integral down here. So this is just a constant, and that's why I use this proportionality sign, which is known and loved by all physicists, right? So the probability, the conditional probability that we're interested in from Bayes' theorem is proportional to the product of the likelihood density and the prior density. That's Bayes' theorem. It's exactly the same concept as Bayes' theorem for densities, for events. And by the way, Bayes actually figured this out in a specific question. He didn't even write it this way. This was too easy for him. He actually figured this out. He figured it out even before integral calculus had been invented. That's what a genius he was in the mathematics of what he did. And by the way, I forgot to mention that Bayes actually never published that particular paper. The one that was, there was two papers that I had in italics on this slide here. Let's see if I can go back. This paper here is the one where he presents his theorem, but it wasn't him. It was published in 1763. He died in 1761. So it was his buddy Richard Price who went in front of the Royal Society and presented the work that Bayes had done. But he said this is all Bayes' work, and that's why it's called Bayes' theorem and not Price's theorem. But Price presented it.
So Price was also a nice person.
Well, he was buddies with Bayes, so he had to be nice.
Good point.
Yeah, yeah. But otherwise, I wouldn't know. But I used the Bayesian method to figure that out. All right. So everybody okay with this? I think we're going to run out of battery on the pointer, so I'll go to the keyboard for a little minute. Yes, sir.
Yeah, maybe this is kind of a pedantic question, but
Those are good too. No judgment.
when you mean like belief in probability models or Bayes, I mean it's not like believing that Bayes' formula is correct or something. I mean you're talking about like a belief that your probability model like actually explains something real.
Mhm.
So that's the belief you're talking about here, not like the belief that you can calculate something, but that your understanding of your model actually captures.
Yeah, I think-
reality that
that's right.
displayed.
I should not have written belief in probability modeling. That's too general. What it really is, it's a belief in a specific probability model for every problem you're looking at.
Okay, because I guess this is kind of like a question about, maybe I'm having a difficult time sort of conceptualizing the difference between these things. So like in the frequentist one with your second example, right? I mean, or with the example that you get on the next slide is like the frequentist approach would be, let's say, run experiment A. Right, see if it happens. Right?
Yeah, I mean, in order to get an actual, so here's the thing, in order to get an actual probability which is precise, which is given to you by Bayes every single time,
You run experiment A many times.
you have to, not many times, you have to run it infinitely many times, otherwise you're not gonna have the type of precision that you would get from a mathematical axiomatic system like the Bayes theorem. So this is an axiomatic system, you have to believe in the axioms of probability, you have to set up a probability space, you have to set up your events, you have to figure out models for those things, for the likelihood, model for the prior, then it helps you compute the probability that you want, and then you're gonna believe in all those things. And if you believe in the axiomatic system of probability theory, which was invented around the time of Bayes, and if you believe in the models that you've decided to use, then the answer is always exact. There's no, it's always exact, there's no arguing with the answer. But in frequentist, in order to get to the same level of confidence, of like 100% absolute confidence in your answer, you have to repeat your experiment a zillion times. That's my opinion, anyway.
That's your belief.
It's my belief, yeah. And I mean, and since I'm an atheist, it's very convenient for me to say that, you know, I believe in Bayes.
How do you, right, one of the things that I always find confusing about Bayesian statistics is that you have to choose a model for both the prior and the likelihood of your data or of the things that you want to model. I think just echoing the idea of like belief, right? Like, how do you know that your assumptions about the prior and the likelihoods are reasonable? Like, how in practice, like how do you go?
Okay, so you know, Ms. Simpowski will show us, and I'm going to try to show you, but I'll run out of time, so I don't have time to show you. But she'll show us that there's things that you can do if you have some hesitation. So like the biggest hesitation is, oh my goodness, you know, like we're in nuclear physics here, like there's 20 different groups and they all have a different model for the same thing. Like they're using different principles. We can't really say one model is better than another. Like it's even worse than that. It's not like we think among these 20 groups working on this one question, one of these groups is better than the other. If we believe that, we can use the so-called Bayesian model averaging. So there's three slides in this presentation that you can look at later. The first one explains Bayesian model averaging. That's straight Bayes, where you're in a scenario where you have 20 groups of people working on the same problem, coming with the same answer, and you know that one of them is going to be better than the other. Or maybe there'll be have 3 of them that have the same likelihood of being the best. And you know it. That's Bayesian model averaging, and there's a method for that. Bayesian model mixing is much more subtle because it says, no, we don't know. None of these 20 groups know the truth. Actually, I hear this a lot from hanging out with nuclear physicists, is that this model is missing this type of effect. That model is missing this type of physics. There's missing physics in every one of these models. So none of them can be the best. None of them can be the best. We're gonna have to try to combine them in order to come up with something which is better than every one. That's Bayesian model mixing. And that's I think in my opinion, the easiest way to overcome this notion of modeling uncertainty. So modeling uncertainty is what you're talking about. You don't have to believe in the models. You don't have to believe in a single model. You can believe in 2 different models or 20 different models. At some point, you're going to have to stop looking for other stuff and believe what you have in front of you. But the uncertainty that you have about all the choices you could possibly make can be dealt with using Bayesian model mixing. Yes.
I want to comment, Edgar. I think your question was more on the how do you know that your modeling of the uncertainties, not the physical models themselves, is something that actually makes sense. Was your question more on that?
It's the no, it's the probability model.
Yeah. It's the probability model as in, like
The functional formula, the likelihoods, the uncertainties, the etc. I think Frederi Viens.
oh, okay.
Yeah, it's called. I mean, in other fields, in fields of insurance mathematics, which is another field, we call that model ambiguity. So to distinguish, because there's two different levels of uncertainty. There's the uncertainty because the model is a probabilistic model. And then there's another completely separate level of uncertainty, or at least on the surface it looks completely separate, is that we're hesitating between several different approaches, which leads to several different probability models. That's model ambiguity. Thank you very much for those great questions. That was great. Thank you, sir.
You have 15 more minutes.
Yep. So I was going to present something on Blackboard, but I'm going to maybe leave it as a tiny little challenge for you all to do. So let's go through this. Yeah, the whiteboard there, or the.
That could literally be one of the challenges for the practical section.
But I mean, literally, this is so. I don't mean to be demeaning, but I have to say this because I believe it again. That there's an equation here which is trivial because we'll get to it. It's just what Bayes tells us. And an equation down here, which is what you get when you play with this equation for 3 minutes, and then you complete a square, and you get here. The challenge is to go from here to here. And I claim that if you're really good at completing squares, you can do that in 3 minutes. It might take another 2 minutes to actually recognize what you're looking at. That's not a calculation. That's just recognizing what you're looking at. If you look at and you recognize, there's no calculation involved. It's just recognition of a formula that's in front of you. So all told, if you're really fast, you can do this challenge in 5 minutes. But it might take you an hour just because you have some modeling ambiguity in your own skills, but the skills needed for this particular challenge to go from this line to this line, these are skills that people learn in high school. So not to be demeaning, but it's conceptually it's complicated. Mathematically, it's trivial. It's trivial. Yeah, everybody heard of this concept of completing a square? And if you haven't, I will explain it right now. Raise your hand if you heard of completing the square. I'm getting about half of the room. Okay, this is what completing the square is. All right, so don't take this the wrong way if you have done this before and you don't know why I'm explaining it. You know the formula a plus b quantity squared equals a squared plus 2ab plus b squared. Well, if you have a squared plus 2ab plus something else, you can switch things around so that you can make it into a square, and then there's something else you have to subtract, and there'll be some term left over after you've completed the square of the a and the b, because you have a formula with an a squared and a 2ab. That's the beginning of your quadratic formula, quadratic expansion. Just whatever's missing, you deal with it later. Just create your square, and you'll have something left over. So that's called completing the square. You guys have done that in high school, am I right? High school, right? Is it done in high school anymore?
Yeah.
Yeah. Okay. Yeah. I heard now that we dropped to the lowest level of reading and writing arithmetic in like I don't know how many decades. But anyway, yeah, completing the square. It's a thing. So so here's a linear model. Let me just go back to this. Yeah, so this might be another challenge for you to look at on your own, but it's actually even more trivial than this one. So let's just look at this one carefully. This is the simplest model we can come up with in statistics that's kind of meaningful. I'm changing the notation here. Instead of having an x and a y, my x is really the beta. Our x of interest is this coefficient beta. Linear modeling in statistics is you have one variable that you observe, let's say call it y prime, and that's the explanatory variable. And then you have one variable that you explain, that's the capital Y. You also observe it. So y and y prime are two pieces of the observation, like boldface y or something. And so how do you explain y with y prime in a linear way? Just, is there a number that relates those two things like that? Well, yeah, sure, except there's some level of uncertainty here, it's statistical uncertainty. And so this little epsilon is what I like to call standard normal error. So capital N stands for the normal distribution. So I'm hoping that folks know what the normal distribution is, but if you don't, it's a bell curve, right? You've heard of normal distributions, am I right? Yeah, it's like not a secret, right? So if you have a normal distribution, a random variable epsilon, which has a normal distribution with variance equal to 1, and you multiply it by the number sigma, then the variance of sigma epsilon is equal to sigma squared, and it's still a normal variable, so it's got that same bell shape, except it's maybe squished if the sigma is smaller, it's maybe spread out if the sigma is bigger than 1. And in case 1 here, which is this slide, let's assume that we're super confident about the uncertainty level sigma, and people like to call that sigma, they like to base an error bar. I crossed it out because I don't like the term error bar, but I don't know if physicists love to use it. It really depends on this level sigma. The question is, we should estimate beta. It's our x of interest. Instead of calling it x, we're calling it beta. As we're doing Bayes, we need to choose a prior for beta. Let's use this one. So we say that beta at the prior level, we believe its density is normal, and with mean 0, let's say, to make things simple for this example. And variance equal to sigma beta squared. So standard deviation sigma sub beta, that's another standard deviation, not the same as this one. There's 2 different sigmas now. This is the uncertainty in the prior that we have, the uncertainty in the model. This is your likelihood equation. It's your likelihood because it relates beta, which is our x, to the observation, which is y prime. So likelihood up here, prior down there, linear models are a likelihood, modeling y prime, relating it to beta. We happen to observe two values for y and y prime. I call them little y star and little y prime star. The question is to find the density of beta given this observation. Bayes' theorem says all you have to do, this is, I remind you that this is just, it's the bottom line here on this slide. You use that bottom line, and this comes out. The probability that you're interested, assuming that you know what sigma squared is, and that you have your observation there, given all this information here, the density of beta is the product of the normal density, this first one. You see here, this normal density here, this is a normal density. Everybody who's seen the formula for the density of a normal? I think this is well known, right? So this is the normal density. You know, it's the one that would be, if we go back to the previous slide, it would be this thing right here, this prior. Right? So then the prior, this is the normal density for the prior. This is the normal density for the likelihood. You just model, you solve for your sigma epsilon. It's y minus beta y prime. It's normal, so you get this density here. That's for your likelihood. So you literally only just multiply your prior density by your likelihood density from this model for the likelihood and this model for the prior. Literally, you're just writing two formulas down by multiplying one by the other. There's no math here. Just writing down formulas and multiplying them. That's it. We are done. That's Bayes' theorem. There's nothing more to it, except we would like to know if we can recognize and maybe even sample from this posterior density. We look at this nasty looking formula and we ask ourselves, what kind of density is that? Well, the density, what do you mean density? Density with respect to beta. All these things are fixed. You've used them as fixed parameters, these three things. Beta is the one that you're unsure about. You're trying to find the density, the probability density. For beta, we look at this horrible mess and we ask ourselves, does this look like something that we know how to sample from? Sampling from means you use a random number generator in your computer, ask it to pull out a value from this particular distribution. That's called sampling. Everybody okay with the concept of sampling? For our purposes, that's what it is. And so we would like to be able to sample from this mess right here. Well, we can't tell. But hold on. Beta is the only thing that matters. Well, there's a square there. See it? Yeah. You expand this square, there's going to be a square here. You're also going to get a 2 beta times y prime star times y star when you expand. So that's a linear term in beta. So you have a quadratic term in beta. You have a linear term in beta when you put these two exponentials together. Yeah. Bring it all together because exponential is multiplication of exponential is additive in the exponents. Everybody knows that, right? Yeah. It's also high school. So we have a quadratic form inside our exponential. That means we can complete the square. When you complete the square, which I was going to do on the board, but because I talked too much about Tunbridge Wells, I'm not going to do it now. You complete the square and you find this. So the challenge is complete the square over here and make sure that this is actually exactly equal to the density of a normal where you recognize its mean, which is the number that's going to come after the minus sign inside the square after you've completed it. And you recognize the variance, which is the number that's going to be the denominator after you set it up correctly. You recognize those two things, that's it. You recognize those two things inside your quadratic formula, inside the exponential. And whatever's in front won't matter because there's no betas in front, so it's all proportional. You can drop all those constants that are in front of the exponential. Beautiful. And you'll recognize that it's normal. And the mean turns out to be y star times y prime star times the so-called likelihood precision divided by the posterior precision. And the posterior variance, which is your denominator after you complete the square, is one of the posterior precision. What do I mean by those things? Well, the likelihood precision, I didn't write it down. Have you guys heard of the term precision? Precision, anybody? Okay, how about variance? Variance? Yeah. Okay, what's the relationship between variance and precision? They're inverses of each other. So if you've never heard of the term precision, well, you have now. It's the same thing as variance. It's 1 over variance. That's it. So precision is 1 over variance. All right. So likelihood precision. So the posterior precision is 1 over sigma squared. I'm sorry. The likelihood precision is 1 over sigma squared because the likelihood variance is sigma. And the posterior precision is this formula here. It's the sum of the prior precision on beta and the likelihood precision multiplied by y prime squared. That's the posterior precision. It just turns out, you plug those things into here, you get this formula, and we're done. And so I think I maybe have one more minute, Dr. Julian?
7 more minutes.
7 more minutes? So any questions on this slide before we move on to maybe the next one? Yes, sir?
You chose your requirement on data centered on zero, and I'm assuming in this case it becomes from some like background and knowledge about what data should work.
Exactly right. I was doing what I was hoping not to do, which was to zoom through this slide, but you're exactly right. How do we figure out? So here's a method which I like to use. Like you go, maybe you have the knowledge yourself, and that could be the background knowledge, or you go talk to people who have the background knowledge and ask them, how sure do you think you are? Or you go and look up you look up the error bars that people have published in their papers, right? Like, or you look at the discrepancy between values of data in 2 different papers using 2 different methods. Like, in fact, writing a paper with Dr. Giuliani and a professor at Ohio University right now on this topic. Like, you can look at 2 different papers come with 2 different values of data using their methods. The distance between them is this number, and then they have their own little error bars, and the error bars are like smaller than the difference between those 2 datas. Then you would say the error bars, the uncertainties that these people are published are way too low because they disagree on the fundamental central value. That's the one which tells you really how uncertain we are in the nuclear world. Take that value, whatever value you're comfortable with in terms of how uncertain things are. That is a value that you can actually literally stick into, you square that value, and that's your variance. And if you're uncomfortable with that because you think it's not conservative. So I'm a liberal, and in statistics, you always want to be conservative. If you think it's not conservative enough, multiply the number at the variance level by 2. If you really want to be super conservative, because grandpa, whatever, by 3, and you'll be fine. Does that make sense? So, and people use these rules of thumbs all the time, and there's no shame in doing it. And I try to write it into papers whenever I can, and sometimes it gets past the referees, and then I'm happy.
When you don't have a previously existing paper where you're testing some model or something like abstract set of parameters that you don't have any kind of prior data on.
Yeah, that's a little tougher. So then you have to use your own judgment, and that's when people will start saying, well, you got to use uninformative parameters, uninformative priors. Well, when using a normal prior, there's no such thing as uninformative. It could be weakly informative if the variance is huge. And so, and then what you could try to do is, because at that point, the prior information that you don't really have isn't really going to influence your answer in Bayes. So you got to do what you got to do. You can set it up with a fairly large variance because you think it'll be safe. You get an answer, then you try to double that, see if you get a similar answer, and then you try to multiply it by 10, see if you get similar. You multiply it by 10,000, that's going to break, and Bayes won't be able to tell you anything at that point, right? So that would be like, I would say, trial and error. And in applied work that we're doing, this is totally okay. But it's always good to, there could be another reason, like maybe your problem is similar to another problem where we know the uncertainty levels, and then that's going to help us, it's not the same problem at all, but it's, we're having the same types of difficulty. So maybe that's where we're going to find out how much uncertainty we think we might have. That's it.
And I want to comment on that. If you're unsure, but people that might have some intuition, bringing them to the team is a fantastic thing to do. And that is going to be a theme on this summer school on why it's super important that you make multidisciplinary efforts with experts and people that might know more about the problem. You might not have a prior idea, but they might. And working collaboratively is the way to go. 4 more minutes.
Another thing I wanted to add to that, and kind of opposite of the question I asked before, one of the best things about Bayesian uncertainty modification is that you make it very transparent what your modeling errors are. Like, it's very transparent, like, okay, this is my prior information, and this is why I believe, again, that the variable that I'm looking for should be around this distributed in this way. And if you get some answer, it's very clear, and someone else is thinking, hey, I think you didn't model your uncertainty correctly, they can point out exactly where you might be making that mistake, and then correct it and make a different model. So, it's a feature of the theory, I would say.
Feature, yeah.
You could have it as tiers where if you have a prediction, for example, a theoretical prediction 20, 30 years ago, is just a prediction without uncertainties. That would be like tier 0. Tier 1 will be you make a curve and you put some band or some error bar, but you don't tell anybody where that came from. You just use some weird algorithm. And tier 3 is like you made it in a lazy way and you do state this is how this band came to be by assuming A, B, and C. And now as Edgar says, somebody come and say, actually, let's modify this particular.
Yeah, that's all part of scientific reproducibility. You know, we have a reproducibility crisis, you know, in our world today, and a lot of that is due to p-values, which were invented by Fisher. So, yeah, so that's what we do Bayes. You know, p-values in Bayes are just really intuitive. You don't even have to call them p-values. You just compute probabilities of interest, and then you're done. So, this is the second challenge. Case one that we just looked at. We assume that we know the sigma in the likelihood models, and then we find out that beta is normal. It's conjugate to the likelihood distribution because the prior and posterior are in the same class. So there's this term conjugate, so you can see coming back in this summer school. So that's when sigma is known. The conjugate prior for your beta is normal, and you get a posterior, which is also normal. In the case, so that's what the notion of conjugacy means. You try to set things up in such a way that the prior and the posterior are in the same class of distributions. Mathematically, it's very useful. And you know, there's not really a great physical reason to do it, but you know, Bayes is so robust that the choices that you make on your priors in terms of what type of distribution you want to use, it's so robust that it usually does make a big difference. So you might as well use the conjugate priors, might as well. So in the second case, now you assume that beta is known and you want to estimate sigma squared. Question, can we find a conjugate prior for sigma squared? Answer, yes. It's called the inverse gamma, also known as the scaled inverse chi squared. Your challenge is to go through this slide and understand how it's done. It's easier than the previous challenge. This is freaking easier than it like sounds harder because these are weird, super weird distributions. But it's actually easier. Just go, it's all here. There's nothing to do. The challenge is to read this and make sure you understand line by line. That's the challenge. It's all there. And then once you had case one and case two dealt with, as we just have, where if we assume that sigma is known, we can compute a posterior for beta. If we assume that beta is known, we can compute a posterior for sigma squared. Once we have dealt with these two things, usually beta and sigma squared are not known. Both of them are unknown. And so then what do we do? So that's the big question. How do we combine these two calculations when both of these two things are unknown? And the answer is, it's simple. All you do is you do the sampling the way that we have it with posteriors, then you iterate. You pretend like sigma is known. You sample beta. Pretend like beta is known, then you sample sigma. You do that iteratively by remembering what your other samples were every time. You have to initialize, but after you initialize, you just use the previous sample every time you think that one of these things is fixed. That's the numerical method. That method is a Markov chain Monte Carlo. Everybody heard of Markov chain Monte Carlo? Yeah, that's what this is the simplest example of a Markov chain Monte Carlo for Bayes. It's called the Gibbs sampler. You've maybe heard of the Gibbs sampler, am I right? Heard of the Gibbs sampler? I think Dr. Giuliani will show the Gibbs sampler is the simplest Markov chain Monte Carlo method. It works really well for linear models. Dr. Giuliani will present something which is one step above, which is called the Metropolis-Hastings method, which is a variation. It's an improvement on Gibbs. It's an improvement on Gibbs. So try to understand this Gibbs because that's an improvement, and that's your challenge. Thank you for listening, and remember that Metropolis was a real physicist. He worked in the 1950s. He had a wife whose name was also Metropolis. Yeah, I think. Is that right?
I don't know.
I don't know.
Yeah. There was a husband and wife team. They were working on the Los Alamos project. In the 1950s, they kept working because after you work on Los Alamos, of course, you can keep working. And the Manhattan Project in Los Alamos, Manhattan Project. And then the paper that we quote, I forgot how the story goes, but she didn't get proper credit. Does that surprise anybody? Yeah. So that's the story about the group that was working with Metropolis that we used to.
I read that at some point.
Yeah, it's true. Thank you all very much, and apologies for going over.
Thank you so much, Frederi. This was fantastic. I enjoyed every minute of it. So, folks, we are in our break time. Let's try to be here back at 10:30. There's going to be coffee and snacks and everything. You can leave your computers and everything here. Enjoy your break, and we'll see you in 25, 30 minutes.
Before you enjoy your break, so after dinner, if you're planning to have dinner.
Yes. And register for the forum if you have it.
One thing at a time, one thing at a time.
That's right. And I'm like, yeah, it's going. How are you? Yeah, we're going to be down on doing drive. Yeah, and I'm going to put you know where I'm yeah. We'll actually do that right before the ball gets free.
Yeah, which kind of why.
Leave it up, leave it up.
Like, I haven't done this
for
in minutes.
Yeah.
Because like, they mentioned planner distribution, but isn't, I thought it was probably.
Soon, people, we're going to be on a break. Go grab your coffees, your snacks, and we'll be back here in 20-something minutes.
So, your model, for instance.
You wouldn't let me log on.
The beta is the parameter, and it's a number, we just don't know what it is. And we're gonna look for its.
Forgot to have me
So.
have some opening.
On the first slide, I was wondering why you. I understand some strength of silence.
Point estimation.
He was.
Yeah,
because
full
it was
plan.
2000.
Yeah, maybe that's what they were talking about.
I want to go over this too quickly, so,
All I did was hold.
full price distributions that will say, anytime you have a model,
You're going
like this, there
No,
are some shares, this one has two parameters, beta and sigma. I guess base will give you the full distribution of probability density of both beta and sigma. Actually, the better for talk about here, the joint probability density.
You know.
And so by the half, we're gonna get a density for these two numbers.
Whenever we will be.
And that's the distribution.
Yeah, that makes sense. If I get any betas.
No, I would disagree with that. There's one beta. It's random as far as we can tell. I mean,
Because I
it's another thing which I didn't have time to talk about, which is the property twins.
Computers is what they
Forum about that and get IT to help me with the sound, right? Like, scroll through, look at all the nonsense that are there, I can't recommendation. Because I think Kyle Duffy has to.